In this video, we'll continue to look at the compound interest formula, and we'll also be using logarithms to solve for time needed to reach a savings goal. So here's our first example. If you want to save $5,000 before buying your first new car, and you have $3,000 right now to invest at 3% interest compounded monthly, how long will you have to wait? Okay, so one clue as to where to start is this phrase, compounded interest compounded monthly. And that tells us which formula to use, and that would be the one that deals with compound interest. So let's use A equals P times 1 plus R over N to the NT, and then let's see if we can use that to get to what we need to know. Alright, so we're trying to solve for how long we have to wait to reach the savings goal. So we actually need to solve for a time, for t. So hopefully we know all of the other information in this equation, or else we can't use it. Okay, so let's start with the future value. Right, this is going to be the savings goal. This is where we want to be at the end of that time period. And that would be the $5,000. Okay, that's the amount that this person wants to save. What would be the principal? Well, that's a starting amount or an amount that's invested. So that would be the $3,000. Okay. Then we have 1 plus R over N. So we need a rate and a number of times per year that interest is compounded. So we know the rate, it's 3%, and we know N, it's compounded monthly, so that's 12 times per year. And then the exponent would be 12 times, and we don't know how long we have to wait. That's what we're solving for. Okay, so that's a t. Alright, so the next step is to simplify as much as possible. So let's see if we can work out any of this this over here on the right side of the equation. Alright, so let's find what is 1 plus 0.03 divided by 12. Okay. And that does work out evenly. Okay, I don't need to round to figure that out. And that's 1.0025. Okay, now using order of operations, we can work the parentheses first. The next step is to do the exponent, and I can't actually do that because I have a variable in the exponent. So I actually can't go on. A common mistake here is to multiply 3,000 times the parentheses next, and that's incorrect because it's going out of order for order of operations. We can't multiply before we do exponents. So this is as simplified as this equation can be. The next step is to start solving for t. So let me walk you through the algebra of this, and you don't need a complete comprehensive understanding of logarithms, but we just need to understand them enough as a tool to be able to solve this kind of problem. Alright, so if you can follow along with this and do an example that's basically the same with different numbers, then that's all we really need to do with logarithms for this course. Alright, so the next step is to start solving, and we go backwards order of operations when we're trying to move things from one side of an equation to the other. Okay, so my goal is to get this t by itself, and I have something with it in the exponent. I have a base to the exponent, and then I also have this number that's multiplied. Okay, so if I were to work this out using order of operations, the last step I would do is multiply by 3,000, so that's going to be the first thing that I move to the other side. Alright, so next step, divide by 3,000. Alright, and then that's 5/3, which is a repeating decimal, so I'm just going to leave it as a fraction in lowest terms. Okay. So now the next step is to try to undo this thing that's at the base of the exponent so that I can get at that 12t and solve for t. Alright, so this is where we need logarithms. Basically, logarithms are the inverse of exponents. Okay, a logarithmic equation will undo, or is the inverse of an exponential equation. It's similar to the way that multiplication and division undo each other, or addition and subtraction. Alright, so if I want to get rid of this 1.0025, I can't just divide by it because it's not multiplied times 12t, it's raised to the power of 12t. Alright, so here's the word logarithm. Okay, and we call these logs for short. Okay, log, and you should see a button on your calculator. There's one that says log, and then you have another one that says ln, and that's another special type of logarithm. Now every logarithm has a matching base that matches whatever it's trying to undo. So what I want to do, the ones on your calculator, if you just see the log button, that's a base of 10, and that undoes things like 10 to the x power, or in our case like 10 to the 12t, it could undo that. But it can't undo something that doesn't have a base of 10. So instead what I need is a log with the matching base. So let me move this over. Okay. I just need a little more space. And in front of that, I'm just going to write log, okay, to indicate a logarithm, and then real tiny as a subscript, I'll write whatever that number is, what kind of log it is, 1.0025. Same thing on the left. Okay, so the same rules apply for logs as with the rest of algebra. If you do something on one side of the equation, you have to also apply that to the other side. So on this side, I'm going to apply that log base 1.0025. Okay, and right now we don't really know what that does. This is just a technical way of writing it. And then here is what it does. On the right hand side, that serves to undo this base. It basically cancels it out, and it also brings this 12t down out of the exponent and makes this a normal size, just a 12t on the right hand side of the equation. Okay. Now a log is like a function, so sometimes we'll put it in parentheses, all right, whatever comes after it. Okay, so I'm applying this log to the 5/3. If you've taken algebra, you may be familiar with things like f of x, all right, or maybe like f of 3, we can apply functions of a number, things like that. Okay, so it's kind of similar here, though just the function is a log instead of a generic function. Okay, so we need to know what to do with this. There isn't a log key on your calculator, so instead we have to convert to the logs that we have, and you can use either the log base 10 or this natural log. So I'm going to go with the log base 10, and here's how you convert this. This expression on the left of the equation is the same as a log base 10 of the big number 5/3 divided by the log of that little number, okay, 1.0025. Okay, so that's it's called the change of base formula. We won't get into a proof of that, so we're just going to accept that as a rule and use that. Okay, so let's try it out. Okay, so on your calculator, find that log key, and you would type this in. Okay, so you would do the log key, and it may pull up a parentheses depending on your calculator. You may also have to type the number first and then hit the log key, depending on your calculator. Alright, so mine, I enter this first. Alright, and if you hit enter at that point, alright, you get a long decimal, 0.0010843, etc. I want to keep this as accurate as possible, so I'm also going to then type the division sign before I hit enter and divide by that other log. Okay, so divide by the log 1.0025. Okay. Oh, sorry there. Log 5/3, that's what I need in the numerator. Okay, and that's a different number. So the log of 5/3, 0.221848, etc., etc. Okay, now when I enter the whole thing, let me do that now. Okay, so the two logs divided, and that gives me 204.5855556. Okay, and I'm going to try to keep as many of those decimal places as possible. Let me clear this out, get some more space. Okay, so right now I have 204.5855, and I'm going to round that last 5 to a 6. Okay, and that equals 12t. Alright, equals 12t. Okay, so now we're back on familiar ground. This is a linear equation, and just to solve for t, I just need to divide by 12. Okay, so that's similar to some of the other equations that we've solved before. Okay, so we get t equals 17.0487, etc. So I can round maybe to 0.5. This is time, so this is a little bit over 17 years. Okay, and if you want to get into the decimal portion of it, you could try to figure out what month this is, but if you said, a little bit more than 17 years or about 17 years, those would be good answers. Okay, so quite a long time to wait. Notice the interest rate is still pretty low, 3%. Okay, so 17 years to get $2,000. Okay, that's quite a long time. Alright, we'll do one more example. So same idea. You can skip ahead and look at the answer if you like, if you feel like you've got the hang of this, but if you need another example, here it is. Alright, this is Try This One 4 from the textbook. If you owe $1,400 on a high-interest credit card at 21% compounded monthly, how long will it take the amount you owe to double if you don't make any payments? Okay, so let's set this up first. We have the compound interest formula. Alright, and let's start filling this in. Let me do that right away. I'll put the formula up at the top. Okay, so the future value, look ahead at what we want this amount to be. Now this is a credit card, so this would be the amount owed. Okay, and what we're interested in is finding the amount of time it takes for the amount owed to double. So we want to know, when does that $1,400 become $2,800? So that's the future value. And $1,400 is the principal, the starting value. Okay, how about an interest rate? Well, we have 21%. Okay, so that's 0.21. And then the number of times per year that the interest is compounded, well, it's monthly, so that would be 12. And then the exponent would be 12 times t. We don't know what t is. Okay. Alright, so if you remember from before, one of the first things we did was try to simplify the part in parentheses. Alright, and this again works out nicely. If it didn't, it would be okay, I guess, in this situation if you wanted to round. We're going to need to when we get to the logarithms. Okay. This is 2,800 equals 1,400, and then in parentheses 1.1075. Alright, the next step was to divide by whatever that principal number is. Move the principal over. Okay, and we get 2. Alright. So we have 2 equals 1.0175 to the exponent 12t. Alright, the next step is to apply a logarithm so that I can get that 12t down out of the exponent. So the number I'm trying to get rid of is this 1.0175, so that's the type of logarithm that I'll apply to both sides. Alright, a log base 1.0175. Okay, and then the same thing on the right. Okay, so magically that cancels out. We're just trusting that that works. Okay, and on the right, we're now down with left with 12t. On the left, okay, we can go ahead and calculate this. All right, so I need the little formula to switch this over to buttons that are on the calculator. So this is the same as a log base 10, and we don't ever actually write the 10, okay, but you can if you want to. Log base 10 of 2 divided by log base 10 of 1.0175. So it's always the log of the bigger number divided by the log of that little subscript number. Okay, then use a calculator. So all in one shot, I'll do log base 2 divided by log of 2 divided by the log of 1.0175. Okay, so this whole thing on the left gives 39.95398.182. That's a rounded value. That equals 12t. So then the last step is to divide by 12, and I'm getting 3.329498, etc., etc., etc. Okay, so this is time. I'm probably just going to round this off. So this is just about 3 years, okay, or a little over 3 years. Okay, so that's kind of interesting. It's a high interest credit card, and it only takes about 3 years for the amount to double. Okay, now obviously there'd be usually fees associated if you don't make any payments, but you can see that interest would increase rapidly even if you just make a minimum payment or something like that. That might be an interesting question, so I will leave this open for you. I believe you have a homework problem at some point that asks you to write your own problem that's similar to this. Alright, so think of some sort of a future value. We did one with a bank account. Okay, trying to reach a savings goal, so maybe your future value is a good thing. You could do a loan like a credit card or something like that, maybe a car loan. See how long it would take for that interest to increase, okay, to a certain value. Alright, so in this video we've talked about using logarithms to solve to reach some sort of a future value type goal. And this is the conclusion of the compound interest section. So in the next section we'll start talking about installment payments, talking about car loans, and different applications for some of these key concepts that you've already learned.